All right, so let's go through those proofs. Theorem 3.1.A. The determinant of A equals the determinant of A transpose. Okay. Maybe recall our definition of determinant. Determinant of a matrix is the sum over all permutations in the symmetry group S sub n, sigma of pi, +1 if that permutation is even, -1 if that permutation is odd, times a product of some elements, a sub I, pi of I, as I ranges from 1 to n. These will read again, a sub 1 something times a sub 2 something times a sub 3 something up through times a sub n something. The something, the second index, being determined by permutation pi. So in each of those products, you're going to see the first index range from 1 to n in order. In that second index, you're going to see that range from 1 to n as well. I don't know about the order of it. The order is going to be determined by the permutation pi. But 1 will occur in that second entry exactly once, 2 will occur exactly once, and so forth. Remember, pi is a bijection, 1-to-1 and onto mapping of the set 1 through n to itself. Okay. I mentioned earlier, these are coming out of a different reference than our textbook. I've given those, I've taken from this textbook numbers that I ended with a letter to distinguish them from our textbook, Gentle's book, and the numbering scheme I'm using there. Okay, so let's show this property of determinants as relate to transposes. Determinant of A equals a determinant of A transpose. If you remember much from determinants in sophomore linear algebra, this might well be one of the properties. The way we're going to do this is introduce some more symbols. Let's define A transpose to be the matrix with ijth entry B sub ij. In other words, B sub ij equals A sub ji. I think it's a little easier to keep up with what's going on because we want to take a determinant of matrix A, got a definition for that, and a determinant of matrix B. So I need to know the ij entries of matrix B. If you don't like this, then just ignore all the B sub ij stuff. When we look at the transpose, we'll be swapping indices is what it amounts to. Okay. Well, for a given permutation in the symmetry group S sub n, consider one of those products. Right? We're going to add up sigma pi times these types of products. You're going to let that pi vary over the whole symmetry group. A group of order n factorial, so it's a sum of a bunch of stuff. This is the bulk of what you're summing together. The plus sign or minus sign goes out front. Depends on the permutation. Sigma of pi, we call it. Okay, so consider one of these products. All right, pi is a permutation of the set 1 through n. So each index 1 through n appears as a second index in the product and appears exactly once, right? So I, as I said, ranges from 1 to n in order. The second index, pi of I, also ranges from 1 to n. The order, well, that's determined by the permutation. So pi of I tells you which comes first and which comes second. Knowing nothing about pi, I can't tell you much about that second coordinate, but when I ranges from 1 to n, that second coordinate's going to take on the values 1, 2, up through n, although I'm not sure in which order. That's where the permutation comes in. All right, so what we're going to do is try to move the permutation over to the first index. So we're going to take a product from 1 to n of a sub I pi of I and write this as a product from j equals 1 to n of a sub gamma of j, second component j. I know that second component takes on all the values 1 through n. Okay, let's jumble around the order in which you're taking this product by taking whichever one gives us a 1 out in the second entry, this pi of I entry. Let's put that one first. Okay, there's only one of those, bijection. So whatever index you get here in the first position, when you get a 1 in the second position, call that gamma of j. Whenever you get a 2 out here, let's put that over here with j equals 2, and whatever came associated with a 2 in the second entry, call that gamma of 2, and so forth. So do that for all of these entries. So all we're doing is rearranging the order in which these numbers occur by putting them in order in terms of the second index instead of the first index. In so doing, we're jumbling around the first index according to some permutation. Call it gamma. Well, no surprise, and I maybe I put too many details in here. That gamma function is going to have to be the inverse of the pi function. If we get I equals gamma of j, as we're requiring I is gamma of j, then we'll need j to be pi of I. We'll need the second entries to be the same. So in other words, we need this gamma function to be pi inverse. So whatever permutation pi was, this gamma thing that I've introduced is the inverse of pi. Okay, but arithmetically, algebraically, all we've done is write the same bunch of numbers down in a different order. It's an order that gives kind of priority to the second index. Hey, why do you think we're doing that? And I'm going to swap those indices when we talk transposes. So that's why we're going through this. The even permutations in S sub n form a subgroup. A sub n, the alternating group. So the inverse of every even permutation is an even permutation. So I'm trying to find out the relationship between sigma for these two permutations. Yeah, even permutations form a group, so inverses of those permutations are in that group, and so inverses of even permutations are even. The remaining permutations in S sub n take away the even permutations, say n factorial over 2 of those, or the odd permutations, they all have inverses. They ain't even. We've used the even permutations to get inverses of other even permutations. So the inverse of the odd permutations must also be odd. So we get the inverse of an even permutation is an even permutation. The inverse of an odd permutation is an odd permutation. Also maybe an elementary fact from senior level algebra. So when we look at gamma and pi, if pi is even, then pi inverse, that is gamma, is even. If pi is odd, then pi inverse is odd, that is gamma is odd. In other words, sigma of pi inverse, sigma of gamma, is the same as sigma of pi. So this +1 -1 thing that goes out front, whether we use the pi permutation or its inverse, denoted as gamma, we get the same value out, okay? So if we look at sigma of pi, product from I equals 1 to n of a sub I pi of I, remember we started with the product a sub I pi of I, we just hadn't put the sigma thing out front. Let's put that out front now. That's the same as sigma of gamma. Well, sigma of gamma is the same as sigma of pi. Either they're both even or they're both odd. So these things here are either both +1 or both -1. Times a product from j equals 1 to n of a sub gamma of j. Yeah, like we said up here. So all we've said is they both start with a positive or they both start with a negative. And over here, I've written these numbers in the product down in different order from what we did over here. All right, so let's look in terms of the b sub ij's. All right, so this is why we went through all that stuff. It's because I want to reverse the order of indices. If we consider sigma of pi, product from I equals 1 to n, a sub I, pi of I, this quantity here, that's sigma of j, yeah, product from j equals 1 to n, right. Let me relate the b sub ij to this. Remember, b sub ij is a sub ji. I've introduced the b's to reverse the indices. So to find the corresponding b value, what I'll do is reverse the indices, and we'll get b sub j gamma of j, because that equals a sub gamma of j, j. Reverse the order on those indices, that gives you the b's. All right, so let's call this equation star. This has allowed us to take these terms involving the A's and write them in terms of terms involving the B's, the B sub ij's if you like. Now, so if we'll sum over all permutations, the determinant of A is a sum over all permutations. In the symmetry group, those kind of products we had on the previous part. So we're summing a bunch of these. How many? N factorial. It's how many permutations there are in the group. Okay, but we just saw we can take this sigma of pi stuff and write it in terms of sigma of gamma stuff and in terms of the B's, B sub j, gamma of t. But here we've got precisely the same type of thing we've got here. I mean, this right here is our definition of determinant of a matrix, and it reads permutation, sum over a permutation, sigma of that permutation, product of entry sub I, permutation of I. It's the same thing, except the permutation sigma. Gamma. Sigma of permutation, product, instead of I, we use j, but it's a dummy variable, B sub j, permutation of j. So the permutations on the right here, permutations on the right here. That's why we went through all that gamma stuff. But that's exactly the determinant of matrix B, and matrix B is A transpose. So the determinant of A equals the determinant of A transpose, and that was the claim. So transposing matrices doesn't affect determinants. All right, let's do something else to matrices. Theorem 3.1.b says if I multiply a row by a constant, that doesn't change determinants. That does change determinants, but it changes them by a factor of k. That is, if we take an n by n matrix B, we form it from n by n matrix A by multiplying all the elements of one row or one column of A by the same scalar, call it k, leaving all the other rows the same. Determinant of B is k times the determinant of A. So multiply row of A by k, it changes the determinant by a factor of k. Our first encounter with elementary row operations and determinants. All right. Determinant of A, definition, this usual awkward thing in terms of the symmetry group. Let's look at a product again. Product from I equals 1 to n, A sub I, pi of I. There's exactly one element from each row, that is, A sub I, whatever, is from row I. So there's exactly one element in that product from each row. There's also exactly one element in that product from each column. First, we get pi of 1. So that'd be an entry from column pi of 1, whatever that is. Next, we'll get an entry from column pi of 2. Next, we'll get an entry of column pi of 3 up through pi of n. I don't know which occurs when, but I know they're all there because pi is a bijection. As we said earlier, that index I takes on the values 1 through n, each of those values exactly once in order. Yeah, pi of I takes on each of the values 1 through n as well. Not sure about the order, but it takes on each of those values exactly once. So when we do this product, and our attention is on, it's going to be on one of the rows of A or maybe one of the columns of A. This product contains an entry from each row and an entry from each column. One entry from each row and one entry from each column. All right, so if B satisfies the hypothesis that we've obtained it by taking, say, a row of A or a column of A and multiplying it by some constant, then we get the following. All right, so product from I equals 1 to n of B sub I pi of I is a product from I equals 1 to n A sub I pi of I. These are the same except one of them has picked up a factor of k. Which one? Well, if you multiplied row 3 of matrix A by k, then when you see A sub 3 something, that one picks up a factor of K. So the corresponding B entry would be K times the corresponding A entry. The B sub 3, pi of 3, would be K times A sub 3, pi of 3. If it was the second column in which you did that, whenever you hit pi of I equals 2, we'd pick up a factor of K on the right-hand side. So it's a little less tangible when I talk columns because that's the one with a permutation in it. Hey, exactly one of these B sub I pi of I's equals K A sub I pi of I in those sums, as we remarked above, exactly one entry from each row and exactly one entry from each column in those types of products. The others are the same. So n minus 1 times we get equality, and 1 time we pick up a factor of K in one element in these types of sums. Now granted, there's a row where you multiply through by K, but you only pick an entry of that row exactly once, correspondingly with the columns. So when we take the determinant of B, we'll take this sum over all permutations, the usual thing, the definition. Now we'll do the substitution. We know when you take a product of this sort with the entries of the B's, you pick up a factor of K. One of those terms contributes a factor of K over the A terms. We pick it up here. We can bring it all the way out front. K is not an index. It's a constant. Bring it out front, and what you're left with is exactly the definition of the determinant of A. Probably this is an easier proof than if we were to go through and prove this using a recursive definition of determinant. So we have to go through and prove it in terms of induction. And we haven't touched on induction. The argument really is fairly easy. The fact that when I do these products, hey, each row is represented exactly once and each column is represented exactly once. So exactly once in these columns, you pick up that factor of K, yielding a K outside of each of those products, bring it outside the sum, and there's the relationship. Determinant of B is K times the determinant of A. So computationally, that wasn't so bad. Back to the notes. Okay, so we proved those two. A note, let's shrink this a little bit so we can see, maybe see theorem B at the same time. This note says, if a row of matrix A is all zeros, the determinant of A is 0. This follows, say, from the theorem by taking a row and multiplying it by 0. That's not an allowable elementary row operation, but it wasn't disallowed in the way theorem 3.1.v was stated. So if you take K to be 0, take matrix A, multiply one of its rows by 0 to produce matrix B. You know the determinant's going to change by this factor of factor B 0. So in so doing, we'd see that if we have a row of zeros, then the determinant of that matrix must be 0. If we took the entire matrix and multiplied it by a constant of K and took the determinant of K times A, claim is we'll get K to the n times the determinant of A. Where'd that n come from? Because up here, we multiplied one of the rows by K. Down here, you're multiplying the whole matrix by constant K. Or equivalently, you're multiplying each of the rows by that constant K. You want to think in terms of rows to use theorem 3.1.b. And you did that for all n rows, picking up a factor of K to the n. Oh, and anything we say about rows in this environment holds for columns as well. This theorem 3.1.b says rows or columns. If we took that constant K from this little observation to be -1, if I took the determinant of negative A, so I multiplied all the entries of A by -1, you see from this observation with K equals -1, that gives us a -1 to the n outside. The determinant of negative A is -1 to the n determinant of A. All right, so if n is even, the determinants are the same. If n is odd, they differ by a negative. Okay, so we're looking at elementary row operations. We've already foreshadowed what's going to happen. Our first elementary row operation was multiplying a row by a scalar, okay? Non-zero scalar if I say elementary row operation. What else can we do? We can interchange rows. That's what Theorem 3.1.c deals with. And we can add a multiple of one row to the other. That's the elementary row operations. So let's go through a proof of 3.1.c, n by n matrix B, formed from an n by n matrix A by interchanging two rows or columns. Then the determinant of B is negative determinant of A. Okay, this will a little more explicitly get into the permutation stuff. Interchanging rows, for example, could be represented with a particular permutation. All right. So suppose B is found by interchanging, say, the ith and the kth rows of matrix A. Symbolically, choose K to be the larger of the two. If you interchange row I with row I, you haven't done anything, so make them different. And suppose K is the larger of the two. Okay. The determinant of matrix B in terms of the entries of matrix B is, from the definition, exactly this. One little observation. I'm using J as the dummy variable when we do these products over here instead of I, because we have two matrices. I'm going to use I for the A matrix. All right, so if we write one of these products out, of which there are many, n factorial of them, some of them come with plus ones in front of them, and some of them come with minus ones in front of them, but we're looking at a particular product. All right, so we'll write that out, and notice it reads B sub 1, B sub 2, B sub I minus 1, B sub I plus 1, dot, 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 B sub K minus 1, B sub K plus 1, dot, 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 B sub n. So we've written out B sub 1 through B sub n with that second index being pi of the first index. That's how it works. And I've done it that way to call attention to, here's the entry in the ith row, and here's the entry in the kth row. Let's relate those to the entries of matrix A. Well, they're all the same except for those in the ith row and the kth row. So we get A1, A2, A sub I minus 1. Now we don't get A sub I here because we've interchanged the ith row and the kth row. So the B sub I pi of I corresponds to the A sub K pi of K. No, excuse me, A sub K pi of I. Yeah, it's in the same column, different row. A sub K pi of I, and A sub I pi of K down here corresponds to the B sub K. So we've interchanged those I's and K's in the first index only. It threw me for a second. So we get A sub K here between the I minus 1 and the I plus 1, and we get A sub I here between the K minus 1 and the K plus 1. These are the relationships. Okay. To swap these indices, let's introduce a new function gamma. Oops. Define gamma, the permutation in S sub n, as follows. We're going to let gamma do the same thing that pi does, except when we input I or K. When we input when I input j equals I want to get out pi of K. When I input j equals K, I want to get out pi of I. So gamma does the same thing pi does, except we've, in some sense, interchanged the way in which I and K behave. Gamma treats K as if it were I and treats I as if it were K. That's the interchanging part. Otherwise, gamma does, first part, does the same thing that pi does. All right, so where we're getting this gamma function is by first interchanging I and K and then applying the pi. For example, let's let this act on the entry I. If I apply this permutation pi composed with, this is symbol there, pi composed with this transposition of I, what happens to the I? First it goes to the K, and then the pi sees it. So when I input an I get out a pi of K. When I input an I get out a pi of k. And similarly for the other parts. Ooh, I need to figure out this sign thing, the sigma thing, for what we've introduced here. And I see, hey, gamma can be written with one more transposition, the 2-cycle, one more transposition than pi has. Pi can be written in terms of however many transpositions. It takes one more for a corresponding representation of gamma. That is, the parity, the evenness or the oddness of gamma is opposite for the even or oddness of pi. You represent pi as a product of an even number of permutations. You add this one in, you get gamma represented then as a product of an odd number of transpositions. The parities are opposite of the gammas and the pi's. That is, sigma of pi equals negative sigma of gamma. So if pi is even, we get out a positive 1 on this side, and gamma is odd. So this sigma of gamma would be -1. We introduce another negative to get the equality. Since these differ in parity, then their sigma values differ by a negative sign. One of them's even and the other one's odd. I don't know which is which, but I know one's even and the other one's odd, and that gives this negative relationship on the sigmas. Remember what we're trying to show? We've interchanged 2 rows, and we want to show that affects the determinant by a negative sign. There's the negative sign. So it's coming out of this weird even and oddness stuff in terms of this sigma value on that permutation group S sub n. Long story short, there's your negative, and it'll ride through the rest of the computation. All right, as pi ranges over all the permutations in S sub n, gamma also ranges over all the permutations in S sub n. I could view this as one of the rows in the Cayley table, the multiplication table of S sub n. If you're familiar with groups, that's not a surprising claim. If you're not so familiar with groups, well, it's true. So we can either let pi range over S sub n and do things in terms of pi, or we could let gamma range over S sub n and do things in terms of gamma. Just going to pick up some negative signs. All right. So if we take the determinant of matrix B, here's your definition. Remember, I used the J's for the B's. Okay. Definition, determinant of B. Let's write that in terms of sigmas. Gammas. Then the gammas are being defined as related to the pi's in this particular way here. So we pick up a negative every time you use one of the gammas. I've replaced the pi of j with the gamma of j over here. So these are just substitutions in what we've done. Then the determinant of B can be computed as given here. We've got that negative. We can bring that out front. And what's left is all permutations, sigma of those permutations, product from 1 to n, a sub j, permutation of j. This without the negative sign, that's exactly the determinant of matrix A. Except we use i's instead of j's, and we use gammas instead of pi's. But both of those are dummy variables. Okay, so determinant of B is a negative determinant of A, and yeah, ultimately right there, that parity argument, the sigma thing, that's where the negative came from. Okay, so we've shown if we interchange 2 rows, this was an argument about rows, then we pick up this negative sign. The theorem said, or columns. Well, all right, fine. Let's take a transpose of B. That interchanges the rows and columns. If B is formed by interchanging 2 columns of A, all right, the determinant of B is a determinant of B transpose. That's theorem 3.1.A. The first thing we showed with our definition. Okay, well, applying the result here, interchanging 2 of the rows of A corresponds to interchanging 2 of the columns of A transpose. The transpose allows us to say anything you can do with rows, you can do with columns in terms of determinants. So we can pick up the negative sign here. You know, the determinant of A transpose is a determinant of A. And then we can conclude determinant of B is negative determinant of A. even when you interchange two columns. Okay, so not a surprise once we've got that first result shown, that the determinant of A and A transpose are the same. Sure, anything you can do for rows, you can do for columns, because the columns of A are the rows of A transpose. Okay, we got some observations following that. Yeah. Okay, if two rows or columns of a square matrix are equal, then the determinant must be 0. What's up with that? You're asked to give a proof, I guess, in exercise 3.1.a. It's fairly easy. Take matrix A. If it's got two rows equal, say, interchange them. Well, that doesn't change anything because they were the same, but it changes the determinant by a negative sign. So now you're going to require the determinant of A to equal negative of the determinant of A. You did this row interchange stuff, say, but the matrix didn't change because it had two rows that were equal. So the only puzzle here is writing this out with the right symbols, and that's no minor feat with some of this matrix stuff. So we need the determinant of A to equal negative determinant of A. The determinant must be 0. The only number which is its own negative is 0. And similarly for columns, if a row or column of an n by n matrix A is a scalar multiple of another row or column, then the determinant is 0. What's up with that? Well, I could maybe multiply by 1 over that scalar. If one row is a scalar multiple of the other, no, I'll tell you what, let's multiply one of the rows by k, call that scalar k, to make the two rows equal. Either divide one by k or multiply the other one by k, whichever. If one is a multiple of the other, then multiply one of the rows by k, making them the same, making A have a row the same as this modified version of A. The determinants will be related as given above. Determinant of one will be k times the determinant of the other. But when you've done the modification, you got two rows that are the same. If we've got two rows that are the same, then we know the determinant's 0 by the previous observation. So this is just a slightly more sophisticated version of, hey, if two rows are the same, then the determinant's 0. If one row is a scalar multiple of the other, the determinant's 0. Sound familiar from senior level? Sorry, from sophomore level linear algebra? Yeah, if you think how you might calculate determinants, this is no surprise at all. All right, so that leaves us with one row operation, and that row operation is row addition, adding one row to another. Okay, they've stated it here in terms of adding several rows to one row. Let B represent a matrix formed from matrix A by adding let me try that again, by adding to any row of A scalar multiples of one or more other rows. Similarly, correspondingly with columns. Then the determinant of B equals the determinant of A. So we've taken row 1 and we've added to it a multiple of row 2 and a multiple of row 3 and a multiple of row 4. So instead of just adding a multiple of one row, potentially one other row, we've added multiples of several rows. We've added linear combinations of the other rows to it. I think I commented in the past, yeah, we could assume we've only added a multiple of one row. That's how you did it probably in linear algebra. Establish it for that, and then we'd have this result by induction. But let's go through the full-blown claim that they make. All right, so let A sub I and B sub I be the rows, the ith rows of matrices A and B. Label their entries. A sub I, there's a little awkward notation here. That's a vector, right? Yeah, it's a row vector. A sub I is the row with entries AI1, AI2, and so forth. Usual notation. Then, for some natural number S and some scalars, K1 through K sub n, except for K sub S, we have that the S row of B is B sub S equals A sub S, the S row of A, plus K1 times the first row of A, K2 times the second row of A, and so forth. So we've added to the S row of A a multiple of the first row, a multiple of the second row, a multiple of the S minus first row, a multiple of the S plus first row, up to the nth row. So instead of just adding a single row, if you don't like this, keep J as arbitrary as long as it's not S. What we've done here then is added a multiple of the other row, but we've done it repeatedly. So slightly more general than you deal with this in linear algebra. And what we get then is this is the relationship between that S row of B and the S row of A. All the other rows are the same between the A's and the B's. So the only change occurs in that S row. All right, let's go to the definition of determinant, which allows us to express things in terms of products involving indices, and those indices indicate, rows and columns. And we'll just have to keep up with where to put this in the right spot. Okay, take the determinant of B, piece of cake. There's the definition of it, permutations, the sigmas, the products. Let's pull from each of these products the S term. Pull out B sub S pi of S. So then the product becomes a product from 1 to n, except for I equals S. So we got the exact same stuff in each of these. We just factored out in each of these products the S term. You know what that S term is? Yeah, we had this on the previous slide. It was the entries in the S row of A. So we'd have A sub S pi of S plus those multiples of the things that we've added to this S row. All right. So we get this kind of summation here by substituting over what we had on the previous slide. And the story is, and none of these are different. The B's and the A's are the same if you stay away from the S row, which we have in this particular product. One reason to do that. And here we've got a product of everything except for that S row of A. Hey, there's the S row of A there. Let's get this product, let's distribute. Let's get this product together with that term. Okay, it'll have to get together with this stuff too. But I like it when it gets together with that term because it produces this. So do some distribution. Take this product from I equals 1 to n, except for I equals S, A sub I, pi of I. Distribute it onto this. The only thing that was missing here is A sub I, pi of S. There it is. Do the distribution, put this inside the product. Now I can say we've got a product from 1 to n of A sub I, pi of I. The one missing sitting here. It's similar to what we did up here. We pulled it out and we're sticking it back in, but we're in the A setting here. And we got some other stuff going on. Now I have to do some more distribution and I'm looking for familiar stuff. So let's see. Let's interchange these two summations. Distribution, as long as I keep an eye on the variables that change inside those sums, I'll be okay. We've got the sums on the outside, so we're good. Let's interchange the row on those summations. We'll have a sigma of pi, right, times this stuff, right, times this product, right. So we've done the distribution, broke it into two sums. All right, you like the looks of this. That's just a determinant of matrix A. Okay, we're trying to show determinant of B equals a determinant of A. But we got a bunch of other stuff sitting over here. Each of these are determinants of something. We've got a sigma of pi, and then we got a product from 1 to n, A sub I, pi of I, except the S symbol has been replaced with this K sub j, A sub j, pi of j stuff. It doesn't have an S on it because of the symbols we've used, but I'm thinking of, I tell you what, let's define a new matrix, B sub j, where B sub j has, for I equals 1 to n, has the same entries as A, except in the S row, where it has this K sub j, A sub j, pi of j stuff. All right, call that B sub j. So B sub j is a matrix formed by A, replacing the S row of A with K sub j times A sub j. J doesn't equal S, that's right there. All right, so then if I can think of taking this and shoving it in that product as the S term, okay, that's fine to say. Then we've got exactly the determinant of some matrix. Okay, it's a matrix, let's call it B sub j, a matrix that's a little awkward to describe, but it's still of that particular form. If for the S row of that matrix, call it B sub j, we'll define the S row in terms of this stuff here. Okay, now what's up with these B sub j matrices? Well, as long as j is an S, then we got the determinant of B sub j to equal 0 because this has got one row as a multiple of the other. The S row of B sub j is K sub j times A sub j. The jth row of B sub j is A sub j. J and S are different. So we've got the jth row of B and the sth row of B to be the same. I'm sorry, to be one a multiple of the other. K sub j, A sub j is one row, A sub j itself is the other row. So the determinant of B sub j is 0. One of its rows is a scalar multiple of one of its other rows. That holds for all of these B sub j matrices. All these determinants are 0. This summation over all those B sub j matrices, by the way, there's n minus 1 of them, all zeros. And then we can conclude that the determinant of A equals determinant of B equals a determinant of A. So if you add, in particular, a multiple of one row to another row, it doesn't change the determinant. That's way useful in computing determinants. So we've got each of the 3 elementary row operations represented in these last 3 theorems that we proved in terms of how they affect determinants. The row addition stuff doesn't affect determinants. Multiplying a row by scalars does affect determinants, but I can tell you exactly how. So that's the first one we did. It affects the determinant by a factor of k. Interchanging 2 rows affects the determinant by a negative sign. So if you avoided that multiplying rows by constants, and you only did row interchange and row addition, it'd be easy to keep up with how determinants change. They change by a multiple of -1 for every row interchange that you use. So all I'd have to do is count the row interchanges, as long as I stay away from this multiplying rows by constants. I'm not talking about multiplying by a constant and adding that to something else. I'm talking about taking a row and multiplying it by a constant and leaving it there. The only time you'd need to do that is if you wanted to make pivots 1. You don't care whether the pivots are 1 or not, and I don't think you do when you're taking determinants. This is a real streamlined way to calculate determinants using row operations. All right, so next on the menu is the fact that in sophomore linear algebra, you probably had a recursive definition of determinants using cofactors. It was ugly and tedious. This stuff is ugly and tedious. In my opinion, a lot of this matrix theory stuff is not very elegant because it's a battle against indices. Vectors were bad enough when you only had one index. Matrices, they got 2 indices, and they can interact in some oddball ways. But you define this in terms of cofactors and recursion. probably in sophomore linear algebra. I've got a link to some linear algebra notes. What we'll do next, so I'll stop this video here in a sec. What we'll do next is go through and show that that recursive definition you had, expanding determinants along your favorite row or column, is consistent with what we've defined here. What makes a row so seductive in terms of taking determinants? Having lots of zeros in it. The more zeros you got, the better off you are. You good at introducing zeros? Yeah, row reduction lets you do that. But row reduction changes determinants. Yeah, but you know how it changes determinants. So next we'll go through and link together our definition with maybe this cofactor expansion definition you had in sophomore linear algebra of determinants. I will see you there in a minute.